So what's the big deal with today? Well, it could be a drug. It could be a product like that little doohickey hanging on a fence out on some dude's ranch. Knowing how long something's going to last or what is going to be the concentration at a certain time is really powerful stuff and really useful and really applicable. All right? So it makes things that appear uncontrollable, at least you can kind of predict them a little bit for maximum effectiveness, whatever the case may be. So that's what we're going to talk about. And we're also going to talk about drawing some potential energy diagrams for reactions, and we'll see why and how that applies in a little bit. But here's the equations. Now, these equations only work, Mallory, if the reaction is of this form. What does that mean? Little a, big A goes to product. Yeah, all it is you don't have two different things, right? They're just reactants. Little a, what was the word for little a? Stoichiometric coefficient, right? So just a little number to make it balanced. But it looks like this is a reaction that could be a decomposition reaction, or maybe it could be the same molecule colliding with itself and reacting with itself, right? The same type of molecule, same compound, forming product. But regardless, that's how the reaction has to look. And then you have these equations. So it's common. It happens very often. Now, looking at these equations, there's some variables in there that I think you should recognize, hopefully. Jessica, like Jessica Rojas. Little t. By convention, that's usually what? Big T, temperature. Little t, time. Little t, time. And then Genevieve, we've seen the K before. What do we call that K? It shows up in every single one up there. The constant, the rate constant. Okay. That leaves a couple more. Nick, we've got this bracket. And there's a bracket A with a little subscript T, a bracket A with a little subscript 0. What do the brackets? Briefly, we talked about it very briefly once before. The brackets represented concentration. The brackets represent concentration. So if you have the bracket A, that's the concentration of A, whatever that reactant is. But the little t and the little 0, Javier? What's the difference? Anyone know? Which one of them is the original or the initial concentration? The one with the O. But I guess what they're trying to put on there is supposed to be a 0, right? For 0 seconds, right? So the bracket with a little O, that's the original or the initial concentration. This guy is. That means the bracket AT, we really shouldn't say bracket AT, we should say the concentration of A at time T. Yeah, whatever the given time is. That's the variable, T. So you pretty much just say the concentration of A at time T. At T equals T. Okay, whatever the time is. 10 seconds, 20 seconds. They have to tell you what it is. T is. That's very useful. After 6 hours, how much of this reactant is left? And you just plug in with little t into the right equation, whether it's first order, second order, zeroth order. And they have to tell us all that. And then there's one more variable up here, this t sub 1/2. Lewis, you know what they call it that? T sub 1/2. Half-life is what the t 1/2 is, the half-life. So, and we're going to talk about that in a little bit. All it is the time for exactly how much of that reactant to disappear. Half. That's really all it is. Okay. But it's useful, and that's why they have it. So the game is pretty much going to be read the homework question, they're going to tell you first order, second order, zeroth order. They have to tell you that, what type of reaction it is. You go look up the equation, and you plug all this stuff in. So you have to know what each variable represents. You have to know K is the rate constant. You have to know T is time. Concentration A at time T is bracket AT. Original concentration. Know which variable that is. Know all that. You plug it all into the right equation. Get one of these guys. Right? It looks ugly, but it's not too bad. Okay. We take a look at A. Do you recognize Vanessa Vasquez? Do you recognize which equation I was plugging into in A? Which one does it look similar to? Yeah, the first order, the upper left. Yeah, it matches it exactly. And yeah. Oh, Ln. We haven't hit it yet. We're going to get it here. Yeah, Ln is natural log, and we're going to find out pretty quick here what Ln is. Okay, so if we're looking at this equation, Sylvia, let's just make sure we're reading it right. In that homework question, and we plugged everything in, we ended up with this equation that we have in A, this mathematical equation. What was the rate constant? Technically not negative 89. It's just 89, right? Because you plug in the minus signs in the equation. So the rate constant is 89. If you see that, you're reading this exactly right. Okay? So you read the problem, you plug everything in, and we end up with this big mess of an equation. Ray, we got to solve for T. What would you do first? And that little Ln is key here. Someone mentioned it. Someone recognized it already. Natural log. Ln. It's on the calculator, right? And you want. So figure out what this number is first, and then take the natural log of it. Right? I would do that first, too. So 6.3 times 10 to the negative 3, right? Take 6.3 to 10 to the negative 3, divide it by this one, divide it by 3.9 times 10 to the negative 2, okay? And you get 0.16. So I'm not going to skip any steps here. I'm just going to write it all down. Okay. Now I find the Ln button on there. See what it is. What's the natural log of 0.16? Where is Ln? There it is. I got about negative 1.82. You got it? A good deal. So negative 1.82 equals 89. Oh, I forgot my negative sign. Thank you, sir. Okay. Matteo, so you do what to get your T? Divide the... Yeah, divide that negative 1.82 by negative 89, and we'll have it. So 1.82 divided by 89, about 0.02 is my T. Okay? How about Jessica Vaughn? This B as in boy. What are you gonna do first to solve for that variable that you see in there?
Didn't you have to figure out negative 35.5?
Yeah, let's do that first. That might be a good idea. All right, why not? We have to do it sooner or later. Negative 35 times 5. About negative 175. Okay. I think she got the easy part there, Alexa. We have to get rid of the Ln. So we have to remember or recall or find out what the inverse function is of Ln and do that to both sides. To get that, just to make that Ln disappear. What is the inverse function of natural log? It's e to the x. So let's not skip any steps, right? So you can remember this. Let's not skip any steps. Let's raise both sides, right? I'm going to have to write it all out. Otherwise, it's going to be hard to see what I just did. We're going to raise this to the e power, e ln 2.49 times 10 to the negative 5 all over a0. Raise that to the e power. Right? Raise the negative 175 to the e power. And it's just like taking x times 1 over x. You just get 1. So e and ln, the inverse functions, they're canceled out. They're gone. So you end up with just 2.49 times 10 to the negative 5 all over bracket, the original concentration, equals e to the negative 175. Okay? I wonder if I screwed up there. Can I do that on the calculator?
It's just,
Okay. So, now what do? I picked bad numbers here. Not too practical, but mathematically it's going to work out. Okay, so what should we do next? What would you do? Let's pick on Mariella. What would you do next? We want to get that variable all by itself. Yeah, she's doing the x thing, the diagonal. Exactly. Move that up on top, concentration 8 times 0, bring that e down to the bottom. So we'll have 2.49 times 10 to the negative 5 all over e to the negative 175. And you could have plugged in, you could have found out what that number is if you want. We're going to have to do it sooner or later. But we're going to do it now. Whoop. A zeros on the bottom. Okay. So what is 2.49 times 10 to the negative 5? Divide that by negative e to that power. Okay. In fact, it might have been easier to find that number over here so you can see what it is. If you do 175 negative e to that x, 9.96 times 10 to the negative, 9.9 times 10 to the negative 77. Okay. So this e to the negative 175 is 9.96 times 10 to the negative 77. So that is that number. Okay. Final answer, about 2.5 times 10 to the 71. See, so it's, the numbers don't make any sense, but that's okay. That's mathematically, it illustrates the problem. Okay? Yeah. So you might want to just find it right away. Yeah. Yes. Which number?
the last part, the E.
Okay. You plug in a negative 175. Plug in 175. Push the plus minus button. Now you have a negative 175. And then shift e to the x. And there it is. Okay. Make sense? Okay. Let's try some more of these. Because this is the homework. This is the tough stuff. Okay, here's another one. Different equation. Do you recognize, let's pick on Amanda. Look at this equation. 1 over AT, 12 times 18 plus 1 over something. That looks like we're plugging into which one? Yeah, the second order one, right? So this is the question where they had to say second order, and then they gave us everything. So they gave us everything but the concentration of A at time t. So they're asking for, hey, what's the concentration after so much time? Looks like it's after 18 seconds. I changed everything this morning. Waiting to do. Sorry. Okay. Pablo. What should we do first? Yeah. Oh, yeah. See what he's saying? He's going to get a number on that right-hand side. Right? The 12 times 18, added on the 1. Now, there's a trick to this, if you want to know it, to make life easier. Get used to using that 1 over x button on that calculator. It makes things so nice. Because when I do stuff like this, I see the 2.4 times 10 to the negative 4. That's where I start. I plug that in. push the 1 over the x button plus 12. So I start with the 2.4 times 10 to the negative 4. Push the 1 over x button. Okay. And then plus 12 times 18. Okay. So. Okay. Yeah, you have to find it in there. You end up with 4383. So if you're not comfortable with that, just do it in steps. That's fine. Okay. But it's kind of easier. It's less writing. Okay. Okay.
Oh.
And then to add 12 times 18. Then it's already in the calculator, so just write plus and then 12 times 18. Okay. If you want to do it in parts, that's fine. How do we end up solving for destiny? What would you do to finally solve for our answer here? Yeah, the cross thingy again. Exactly. 1 over 4383 equals the concentration of A at time t. And just use that 1 over x. 2.28 times 10 to the negative 4. What'd you say, Nick? You see it? Okay. 1/2. Because this, if it's already in your calculator, just push 1 over x. I don't know if it is or not. But if it was, right? It was. So that's why you get used to that 1 over x button. It really speeds things along. Okay. Here's another one. Mallory, what should we do first? Yeah, let's do that. Let's multiply that thing out there. So we'll have a natural log A at time t, 7.2 times 10 to the negative 3, 0.15 times 8. That's negative, so negative 1.2. Okay. Jessica Rojas. Now what? Can't do the diagonal thing. So take what? Both sides to the... Whatever's going to cancel and make that ln the inverse of it. The e. The e, exactly. So raise both sides to the e. So you end up with that ln's going to disappear. So I'm just not even going to write it. But if I do that, I better make sure I write that on the other side. Right? Raise both sides to the e. Okay. You should probably figure out what that is. So let's make sure everyone's doing this right on their calculator. But you wouldn't... What I would do is I'd plug in a negative 1.2 to the e power, and then take it times the 7.2 times 10 to the negative 3. Do it all in one big step. Okay? But we can break it down. That's 0.301. All right? You should plug in a negative 1.2 and then shift e to the x. Okay. Concentration of A at time t. Okay. Now you got to do what? Do the diagonal. Yeah, bring it up to the top. Okay. You comfortable with that kind of thing? As hard as it's going to get. Alexa, make sense? Okay. Did you get it, Javier? We're good? Half-life questions. Half-life questions. Notice a hint is there's no space to work, so it must be a conceptual question. And it's conceptual because look at all these half-life equations. There's no little t in there. So it's not a calculation question. These questions are mental questions. Yes, you got to be mental to figure these out. Genevieve, it says bracket A0 is 2.0 molar. What's the layman's term for that, Genevieve? Bracket A0? It's supposed to call it the what concentration? The initial, or the original. Exactly. So the initial concentration is 2 molar. The half-life is 5 seconds. What is the concentration of A after, and they give us these times. The first one is 5 seconds. Nick, how much reactant, what's going to be the concentration of the reactant after 1 half-life goes by? You just divide the wrong number. Originally 2 molar, it's going to be 1 molar. Right? Now, I think it's easier if you show the math, though, because you'll see why. Multiply the original concentration times the number of half-lives that went by. That's really all this comes down to. 1 half-life went by, because they said the half-life is 5 seconds. So you get 1 molar. Yeah, they're all modified sooner or later. Things evolve, evolution, right? You biology majors. Okay. Javier, in number 2 here, how many half-lives went by? How many because 20 seconds. Each half-life is 5 seconds. 4 of them. So you have 4 half-lives went by. So I have to have a half written down 4 times. Multiply half by 2, 3, 4. Multiply the original concentration times a half 4 times. And then I'll get my answer. Well, what is it? And then you got to multiply it times 2 more. But, oh, really? It is. Okay, how about, so whatever you get, that's fine. 30 seconds. How many half-lives? 6? Everybody agree? 6 half-lives. So instead of writing half 6 times, probably just write 1/2 to what power? Might be easier, right? They have to write so much. But that's the idea. Okay. That's the idea. So figure out how many half-lives there were, and you multiply 1/2 that many times the original concentration, you'll get the amount left over. Okay. I guess, looking at this, since I like those math equations so much, you can't use this side, the left-hand column of equations, because they didn't tell you K. You can't calculate this stuff. Kind of remember that. Figure out the number of half-lives that went by. How to sketch potential energy diagrams. Now, when they can, and when they have enough money, and when they can make enough money, they do this. Except it's going to look a lot more complicated than an organ. It's these 3-dimensional surfaces with valleys and hills, and it's all with potential energy and how the reaction progresses. What's more natural for something to occur at? Does nature want to be at a low energy or a high energy? Low energy, right? So when you're looking at this potential energy surface, when they're at the peaks, they're looking for valleys, and the lower the better. Hey, something's going to form here, and it's going to be really stable under these conditions, and at this time, and this is how long it's going to take, and it tells a lot of information. So we're not going to get that far, but we're going to have a general idea here. Okay? So on this y-axis is potential energy. X-axis, yeah, time. I wish they would have time, because it would make a lot more sense. At least it's more conceptual. They call it reaction progress. But Jessica's right. It's time. Time 0, and then as the time progresses in the reaction. Okay. The reactions start out far apart, and they're getting closer and closer together, and they hit, collide, make a product, make it a product. So that's pretty much what it means. Endothermic. Lewis, if you have a reaction in your hand, it's in a glass container or something, and it's endothermic, does it get cold or hot? It goes cold. He's exactly right. He nailed it, right? Because heat is a reactant. Remember, exothermic, that's when heat's given off. So things are going to get hot. So endothermic, things get cold. It's sucking up the heat from your hand, the glass, the water, everything. It's sucking up heat. So it's going to have to start out at a low energy, end up at a high energy. Endothermic. Start out low, end up high. Okay? Start out low, end up high. Well, what starts out? The reactants do. So you can write the word reactants, but I think we should be more specific and write down what the reactants actually are. In this case, they're just A and B, so right, A plus B. What's the product? Just C. Yeah, just write C. You write product. Okay, now, you don't draw a straight line from one to the other. They found out that A and B, not only do they have to physically collide, but they have to collide in the right orientation, with the right amount of energy, and if they do that, they're about ready to form product. It's a very unstable situation that they have to overcome in energy. And this hump is greatly exaggerated. You can hardly even see it in real life, but there's a hump there that has to overcome. Now, there's 2 arrows we're going to draw for energy. One is that the energy that those reactants had to overcome, right, to make product. They had to get that much energy in the arrow, right? If they don't have that much energy, there's no way they're going to make a product. And then the other one is, hey, what was the difference in energy between the reactants and the products in the first place? And that's the second arrow. Okay. Which one of those, Vanessa Vasquez, is delta H? Ooh, she got it. It's the second arrow, right? The smaller one. Why? I think the easiest way for me to explain it is we had to calculate delta H for a reaction. And I don't know if you remember, but the easy way to do this was to look up the delta H for all the products in the back of the book. Look up the delta H for all the reactants in the back of the book. Right? You add it all up for the products, add it all up for the reactants, then you did what? You subtracted them. And that's all. So it's just the energy difference between the products and the reactants. That's all delta H is. So we need to be able to label that on these reactions, on these potential energy diagrams. The other arrow, EA. Energy of, does anybody know the word? Or, not energy of, it's easier to say there it is, activation energy. That's what EA is, activation energy. The energy that reactants have to overcome to make products. Do the same thing for an exothermic reaction. So nothing changes on the Y and X-axis. But now, right, things get hot. So you end up at a lower energy because you kicked out all this heat. So you end up way down here. There you go. Just flip. The other guy goes high. You start out with a high energy, end up with a low energy because you had to release all this heat. Things get hot. So A plus B, that's where we start out. C are our products. Draw your hump. Don't draw a straight line. And draw in those 2 arrows for those 2 energies. One has to be the energy that the reactants had to overcome, And the other one was the energy difference between the reactants and the products. So hopefully there's one energy that the reactants had to overcome. And then the other one, there it is, the energy difference between the reactants and the products. So Ray, which one, the first one or the second one there is your delta H, the one on the left or the right there? The little arrow? Yeah, because the energy difference between the reactants and the products is delta H. He's right. So there's my delta H. This little dude must be my energy of activation energy. Okay. Do you remember, Matteo, we mentioned very briefly the word catalyst. I don't know when that was, but what was the big deal? Yeah. Ooh, it can get things going really good, right? It makes things go faster, easier. A catalyst can't change the energy of the product, because that would mean, you have to type in all new numbers in the back of the book. That doesn't make sense. You can't change the energy of carbon dioxide. It is what it is. But a catalyst could do what? Yeah, but how? How is it going to make things go easier, faster? How? By lowering the hump, the activation energy. Lower that hump. Lower that activation energy. That's what a catalyst does. Remember, these reactants have to get closer and closer together, combine, in the right orientation, all these things. Well, what does a catalyst do? Somehow it really helps them collide and react in a much more efficient manner. They collide and they react in the right orientation in the first place. The collisions are much more effective. Okay? Okay. Here's our first question. Jessica Vaughn, we've got, and if they say it's second order, rate constant is 0.225, initial concentration is 0.293. What's the molar concentration of A? 0.4 seconds. So, how would you start with something like this? She says plug in what you know. But you got to plug it into something, though. What's the equation? Oh, good. She says the second order one, the second. Here it is, right? Now, there's two of them, though, Jessica. For second order, which one? Why the first one? Yeah, it doesn't ask for half-life. What are they really after? They want to know the concentration of A. Yeah, which variable? Actually, the original concentration. What's back up here? Yeah, we got to read this more closely. Which variable? You're right. It says second order, so we got the right set. So which variable? AT? Yeah, they're after this dude. Right? Do you see that? They're after that one. Because what is the molar concentration after so much time? That fits perfectly how AT is defined, concentration of A at time t. So that is what tells you which equation you got to pick. You don't have any choice. This one. Okay, so let's copy him down. 1 over the concentration of A at time t plus 1 over the concentration of A at time 0. Okay. Now, we're solving for A at time t, so let's leave him alone. Alexa, they had to tell us everything else. What's the K? 0.225. And we need to know the T. Amanda, what are we going to plug in for the T? Anybody see it? That's 35.4 plus 1 over 0.293. The original or the... Okay. So, Pablo, what are you going to do to solve for concentration A at time t? Oh, he wants to do the 1 over x way. I agree. That'd be faster. Take the 0.293, 1 over x, right? 0.225 times 35.4. You can do it in multiple steps, or start out with the other method, one big step, 11.38. Okay. Regardless of how you do it, you should end up with 11.38. You've seen this a lot. Move along the diagonals, switch them out. 1 over 11.38 is really going to be my concentration of A at time t. I got about 0.088. Take 1 divide, you can do it multiple ways, however you're most comfortable with it. I'm most comfortable taking 0.293, shift 1 over x, I get 1.12, all right? But if you're not sure how to do it, just take 1 divided by 0.293 plus 0.225 times 35.4. Now, Mariella, I'm going to take a point off if you just do this. Why? What's that? Units. What units do you have to put on this? Second? Grams over mole. Grams over mole is molar mass. Seconds is time. Moles over liter. Or, right, big M. Right? Moles over liter or big M. Okay. Now the homework could try to pull a fast one here. Decimate. What if they would have said after 2 minutes? You got to convert it to seconds. How do you know? Pretty much it's always in seconds. Concentrations in moles per liter, or big M. Time is always in seconds. How do you verify all this? You look at the rate constant units. There they are. Right? Yeah. And you can always verify it. Just look at the units for the rate constant. And they'll tell you what the units of time. And it's pretty much always seconds. I know it's always seconds. Okay. All right. Try to set up this one. We have a couple minutes left. See if you can set up this one. Figure out what the reaction is. Or the equation. Figure out what equation to use. And figure out what the variables are, which one they're after. Oh, they say it's second order again. Is it going to be the same equation? It's second order. Yeah, they don't talk about half-life in here. Yeah. Well, they're after which variable? T. They're after T. Now, there's no T in that second equation. Recognize there's a big difference between T and T1 half. Right? T1 half, half-life is not T. So you can't use that one. It's going to be the same equation again. you know everything you need to find. And everything's in there. Solve for t. So what variable is the 6.07 times 10 to the negative 3? AT. Good. There's our K. And there's our initial concentration. Okay, should work out. Okay. So we're about out of time. Come by and be glad to help you out. There's a bunch more questions on here. The solutions are online. Work them out. Be good practice for the homework. I'll be glad to help you out with this stuff.